Okay. So we now have the skill needed in order to calculate some formula masses. But formula masses are not functions, all right? In the end, after about a month from today, well, maybe a bit longer than a month, maybe a month and a half, where we want to be in terms of our quantitative or numerical analysis of chemistry, we want to be to the point where you can take a certain mass of products, right, 2.5 grams of carbon, and do some mathematics. And if we were to combust that carbon, you should, in the end, be able to figure out the mass of carbon dioxide that will be produced. So in the end, as a practical chemical application, or as something practical to chemists, we want to be able to start with masses, weigh it out on a scale, predict what we could get as a product, and then do the experiment and see if we actually get it. That's what really vaulted chemistry into being a real science. I probably told you this story before, but in the late 1600s, early 1700s, Sir Isaac Newton proposed the three laws of motion. And if you've taken physics, you know the three laws of motion that concern forces. And all of a sudden, physics became a great science because you could actually predict what something was going to do if you knew how fast it was going and if you knew what the force was applied on another object and how it would move, like kind of like billiard balls on a pool table. If you know all of the initial conditions, you can do some math thanks to Newton, and you can predict where all the balls are going to be after it's struck. You just need a lot of time and a lot of math. Chemistry was not mathematically predictable in the late 1600s. It still kind of was a little bit of hocus pocus. Those who knew how to do chemistry would mix a few things and get some really neat products, but there really was no way to really predict exactly numbers of what you would get until Lavoisier came along. And I'm not going to get into that in the story. And then Lavoisier got scale, and then, well, not that it was the scale, but a good scale was developed, and he used that to start to quantify chemistry. And that's what we want to do. We want to do the same right here. We're on the beginning of being able to quantify chemistry. The problem is a formula unit and a formula mass is phenomenally tiny. And we can't actually weigh out a single atom or a single ion or a single molecule. So we need to kind of deal with that problem of the smallness of atoms. And the idea that's come from that is something we call the mole. All right? Now don't write this down. Don't write this down. This is just one of those discussion kind of slides. Atoms, molecules, and formula units and ions, they're way too small to see. Observable changes in chemical reactions must involve extremely large numbers of these entities. Billions and billions and billions of them. Therefore, we need a method for counting large number of entities and measuring their mass. The unit that was chosen was something that we call the mole. And it's not like it was chosen, it was mathematically determined. This I do want you to write down. This is the first time you're coming across this number that we call the mole. And that's exactly what a mole is. It's simply a number. It's like a dozen, but it's a lot bigger. And that's essentially what it is. We use a dozen if we're selling corn or eggs or buns, right? Sometimes you can buy a dozen. I guess that's a useful number of things, 12. Who knows why that was, evolved that way, but it must be. There's even a term if you have 12 dozens. Anybody know what that is called? You can buy pencils like this. 12 boxes of 12. Who knows why 12 is so special? But we seem to like the number 12. It's called a gross. You ever heard that term before? Gross? Yeah, it's 12 dozens. Yep. Oh, there you go. We have to mess it up. Add an extra fun to the bag and mess everybody up here. Well, the mole is essentially like that. It's just a number. Now, it's a phenomenally huge number because we're going to be talking about very tiny things. So we call this number Avogadro's number in honor of the scientist who proposed a theory a long time ago which allowed chemists to then do calculations on gases. And when they did the calculations and they wanted to quantify a special number, it was Avogadro's theory, it's actually called Avogadro's hypothesis, we'll encounter it later, but it was his hypothesis that allowed chemists to come up with that value for the first time when they first wanted to come up with a special number, all right? So Avogadro's number, 6.02 times 10 to the 23, is a very special number, all right? And you'll notice it's not like 1 times 10 to the 23. Like I believe the term Google is actually a really big number, right? That's why Google used the term to, for their name. I can't remember what it is. It's something like, oh, we got a numerologist in the room. What is a Google? So it's 1 times 10 to the 100, right? That's significantly larger than this, right? It's 75 orders of magnitude greater approximately. And then you can even add larger than that, a Googleplex or something like that. What is that? That's like a Google to the exponent Google or something like that. Again, oh yeah, it's a phenomenally crazy large number. Now we don't need such large numbers for chemistry. It turns out that 6.02 times 10 to the 23 is just big enough. And again, notice it's not 1 times 10 to the 23, so it wasn't designed to be just a big number. It's actually been designed to be a very specific big number. And we'll learn why they needed that number in a moment once I keep going, all right? So just to kind of put things in perspective, let's talk about measuring things here. And I had a nice table, and I can't remember what I had for the check. But if let's say we're measuring something like length, all right? You guys know what the unit is. What is the SI unit for length? Physicists, if I'm measuring length, what am I putting all of my units in when I'm doing my calculations for Mr. Petrus? Distance, length. Oh man, that's so sad. Yeah, meters. That was painful. Meters. And we have a symbol for that, right? We have the symbol for meters. Actually, we don't call it the symbol is length. The unit is length. The SI, the thing we're measuring is length. The SI unit is meters. We would write it as being meters M, and actually the symbol, that's not what I want to write here. I'm killing this page here. But we might call it D, right? Or we might call it L to represent the length. That kind of look familiar? I'm getting all my terminology mixed up. But if we want to measure length, we want it in meters. The symbol is M. And in an equation, we might see it as a D or an L. Does that sound about right? Okay. And what if we want to deal with time? What is the SI unit for time, that smallest little bit of time? Okay, now we're getting it, Janessa. Seconds, right? We talk about seconds. And the unit, if we wanted to shorten it up, it's S, right? And if we see it in an equation, what's it going to look like? Yeah, it's a T, might even be a delta T, et cetera, okay? What else do we have here? Mass. If I'm dealing with mass, now in physics, they don't use the base unit. But what is that base unit for mass? Yep. Dallas? Kilograms is the unit that physicists like to use. But that's not the base unit. What's our base unit? What's the unit we start with? No. Now you're thinking of something different. You're thinking of force, gravity. What do we want? I just want grams. Grams. So mass, we measure in grams. And we have G as that symbol. And if it's in an equation, what's it normally looking like? Yeah, Janessa? M, it's M. It's pretty well always M, all right? Now, in actual fact, those are our three main units for determining things like physics. All other units can be determined from those units. Your force unit can be written in terms of those. Does Mr. Petters talk about that, how you can write the other units in those terms? Nobody's saying anything. We just had physics. Yeah, again, Alexi's like, yeah. Okay, so let's talk now about the mole. The mole actually measures something, and it has actually been adopted as the SI unit for measuring these things. All right? If we want to shorten it up, we're not very quick as chemists. We drop the E. It is sad, but that's what we do. And in a symbol, in an equation, you're going to see it as N. All right? You're going to see it as an N. It actually represents a number, right? Because like I said, a mole is like a dozen, or a Pinterest dozen, or a gross, or a Google. It's just a number of things. What would we call that? It's not length, it's not time, it's not mass. What do you call it when you count things? Any ideas? Sorry? Yeah, it's just quantity. It's the SI unit for quantity. So if you're counting something, whether it be in chemistry or anything, even in physics, and you are counting a large number of tiny little things, the unit you will use is the mole. It's just simply a big number of things. All right? Now, you guys already know, and I'm going to write it here, and I should make a new sheet. I might do that when I do this afternoon class. But you guys already know that if I want to deal with, say, a large number of meters or a large number of grams, I can use prefixes like kilo, right? And I think I have this on your sheet. Take a look at your data sheet. 1 kilogram can be easily converted back into grams by just taking what that prefix kilo stands for. So if I've got a kilo, what's that stand for in terms of a power of 10? Yep. 10 to the power of 3. So I can put 1 instead of kilo times 10 to the power of 3 grams. Okay? I can do the same with the mole. If I have a very small amount of moles, I could have something like this. What would you call that? That's a lowercase m. What do you think you would call that thing? Yep. That's a millimole. That's a millimole. Right? Just like a millimeter, you can have a millisecond, you can have millimoles. What would that be equal to in terms of moles? 1 times 10 to the, all you got to do is find the prefix, yep, negative 3 moles. So all of our SI prefixes are fair game for these calculations and these questions. You have the data table that tells you what the prefix represents. So if you ever want to turn it back into moles, you just stick that power of 10 on the back end, and then we're ready to do the math. All right? So moles are just like any other of our regular units that we've encountered, except it measures quantity, how many things, and we can use our prefixes on those things. Okay, let's talk a little bit now about, well, here, don't write this one down. I used to define entities here, but I've already done that. 1 mole of Na contains 6.02 times 10 to the 23 Na. What are the little entities that we're counting if we're counting Na? Yep, atoms. Atoms. And 1 mole of CO, carbon monoxide, contains 6.02 times 10 to the 23 CO. What do we call that little entity there? What do we call that smallest piece of a CO? Tyler? It's a molecule. And if I had 1 mole of calcium chloride, it contains 6.02 times 10 to the 23. what do we call the smallest pieces of calcium chloride? Janessa? Formula units. Formula units. And if I have 1 mole of SO4 minus 2, yep, ions. All right? So again, entities can be used in terms of this discussion as well. Okay? So we usually want to talk about moles, and then we want to think about how many entities that represents. And it depends on what the entity is. You don't have to write any of this stuff down. A mole is really a phenomenally big number when counting things that aren't really tiny. All right? If you had an Avogadro's number of sheets of paper and you divided it into 1,000,000 piles, each pile would stretch from the Earth to the sun and beyond. It would be just past the Earth. That's how big of a number it is, and we can really only talk about the little entities when we talk about moles. We can't really talk about anything that is big, macroscopic, we said, where we use the term. We use the term macroscopic to be big things that we deal with in everyday life. This is a macroscopic object. The mole is really useful for microscopic things. Avogadro's number of pennies side by side would stretch more than 1,000,000 light years. In order to obtain Avogadro's number of grains of sand, you would need to dig up the entire surface of the Sahara Desert, which has an area slightly less than the United States, to a depth of 2 meters. Sand. That's probably, grains of sand is probably the only thing that you can hold in your hand that you can see that we would have a mole of on the Earth. You need things that are that tiny, there's so many of them, and we've got such a large desert that we would have a mole of that substance, right, that you can see. An average lifespan of 75 years, a person's heart beats on average 2.84 times 10 to the 9, that's supposed to be 10 to the 9 times. So that's the number of heartbeats, 10 to the 9. The total number of heartbeats in an average lifespan of the world's population would then be 4.3 times 10 to the 2 heartbeats, still less than a mole. Still less than a mole. So it's a phenomenally big number, but we're talking about really tiny things. A mole of water molecules occupies a volume of 18 milliliters. So if we have 18 milliliters of water, we have exactly 1 mole, which puts it into perspective. That's what's nice about the mole. 18 milliliters can fit into, maybe a little whiteout container, might be 20 milliliters, right? That's a mole of water, and that's why we like that number. It's something that we can work with in our hands in the lab. Okay, now I have to introduce you to something called conversion factors. And again, in physics, you may have already learned conversion factors. You may have learned it as what is called dimensional analysis. Maybe at the beginning, I'm not even going to look because you guys don't even tell me. Because one person goes, no, the other person goes, yeah, right in front of each other. It's exciting. You may have done dimensional analysis. I would hope. Yeah, I'm sure. Write that note. Yes, you do want to write that down. Is this an extra one? Yeah. Okay, good. The majority of the calculations that we will do in this course from here to the end can be done using this calculation method called the conversion factor method. When I was in high school and I was taught chemistry, I was taught an actual mathematical equation for each one of these conversion factors that I'm going to teach you. So in the end, you had to memorize a whole pile of mathematical equations. So this is a method in which we can do calculations. me give you a couple of examples of these conversion factors. There's two ways in which we can present a conversion factor to you. I can present it to you as an equality, 1 dozen equals 12 eggs, or I could present it to you as what I would call a compound unit, a unit that contains more than one unit built in. Now, conversion factors can easily be made out of either of these two. Let me give you an example on how we could use this thing. Let's say that I had 375 eggs. And I wanted to know how many dozens I have. Now, for those of you who are mathematically inclined, you've been doing these questions since grade 3. You grab a calculator or you know how to do the calculation. You quickly do the calculation. You put your hand up and you tell me how many dozen it is. Right? Chelsea's already grabbing her calculator. She's going to do the math. And what are you going to do there, Chelsea? How are you going to get that number? 375, and what are you doing mathematically? You're dividing it by 12. And that's excellent. That's good. But we're going to be dealing with some numbers that are really big and really small, and sometimes units that are new to us. And so sometimes it doesn't become intuitive on what to do, how to divide by 12. There's even some of us still probably maybe in the room right now going, oh man, I hate these questions. How did she know we had to divide by 12? Right? And that's fine if that's who you are. Because if that's who you are, I'm going to show you how we know how to divide by 12. A conversion factor, all right, is essentially a fraction. It's a fraction that's been made of the two units. And the conversion factor to convert 1 dozen into eggs looks like this. I actually have two options for it. I could write it like this. 1 dozen is equal to 12 eggs. That's a fraction right there. That's a conversion factor. Or I could write it down as 12 eggs is equal to 1 dozen. All right? All I've done is flipped it over. But what I've done is I've simply made a fraction for this. Now, when I want to use a conversion factor to do a calculation, I have to look at the unit that I'm starting with. I'm starting with eggs. And in the end, I want the units to actually be converted into dozens. So I need to have a number on the bottom of this fraction that contains the unit eggs so I can cancel those units away. And that's how you use a conversion factor. You make a conversion factor just by making a fraction, and you've always got two options. Now, to use a conversion factor, what you do is you look at the unit you want to get rid of, and you want that unit on the bottom, 12 eggs, because now mathematically, when I multiply this and I divide this, eggs cancels away. We're all aware of the fact that, like in mathematics, if I've got 2 times 5 over 7 times 2, what can I do here with this to simplify this? How do I simplify this mathematically? Yep. Cancel out the 2's. They're gone, right? I can do the exact same thing with units. If I have eggs in the numerator, in the top, and I got eggs in the denominator in the bottom, I can cancel them out. Now I just need to state that that is equal to 1 dozen. And if I do that, you'll notice, in order to do this mathematically, I got to divide off the 12. And that'll get it right every time. Okay? Clock's been adjusted. We will actually go exactly right to 50. So I'm going to keep going because of the time change. All right? I can flip-flop this the other way. What if I had 17.25 dozen? What if I had 17.25 dozen? And I wanted to figure out how many eggs I would have. Now let's use the conversion factor. I have dozen here in the numerator of my first number. For those of you who are wondering, what do you mean numerator? A regular number is like saying over 1, right? So what do I have to have down here in my conversion factor in order to cancel it away? Yep. And what number goes with the dozen in my conversion factor? 1. For every 1 dozen, how many eggs are there? 12 eggs. You'll notice at this point, what happens to my dozens? They cancel away, and look at the unit that I'm left with. Eggs. How do I get the number? 7.25 times 12. And that's how I get that. Okay? I can do the same with speed, or any unit that has 2 units in it. Because I can write this down as being 110 kilometers per 1 hour. That's a conversion factor. I can even flip it over depending on what I want to find. 1 hour is 110 kilometers. What 2 units can I convert between with this conversion factor? What can I convert between? What 2 units can I turn one into the other using that conversion factor? Yep. No, I can't do minutes and meters. There are no minutes nor meters in that conversion factor. I cannot convert from minutes to meters. Hours and kilometers. That I can do. So if I said I got to travel 13,000 kilometers, how many hours is it going to take? What do I have to put in the bottom of my conversion factor? What do I have to go into the bottom? Yeah, Janessa? No, because that's not going to cancel out my kilometers. So no, I can't put the 1 hour down there. Yep. No, because I don't have a conversion factor that can change 1 kilometer. No, I can't put that there because that's not what it is. I can put 110 kilometers, and what's true about 110 kilometers? It is equal to 1 hour. Now that will convert into hours. All right? And this is a method we're going to use a lot when we get rolling here. We'll get our conversion factor, and then we'll start putting the calculations together. All right, so no homework for this second part of the lesson. I just wanted to introduce the mole and get us thinking about that. You can finish off the other stuff.